So a good way to tabulate two categorical variables is via SPSS crosstabs. So let's take a look at how to do that in SPSS. We'll recreate this table here. In SPSS, to get a crosstabs, we're going to use our Analyze menu again. We're going to go to Descriptives, and you'll see an option here, Crosstabs, and we'll get a pop-up window here, and you can decide which you would like in your row and which you would like in your column. Typically, if you remember from the Pearson correlation and scatter plots lab, part of this lab, I mentioned what is typical. Usually the dependent is on the y-axis, independent on the x. Similarly, what's typical when you create a crosstabs is to put your exposure on the rows and your disease or outcome in columns. So when you're dealing with diseases, for instance, categorical variable, for example, had heart disease, did not have heart disease, and let's say your independent variable you thought was smoking exposure, yes, no. So those are two categorical variables, so I would put smoking exposure in my rows and I would put heart disease in columns. So typically that's what's done. So we'll do that later on as well, and you'll see it's clear, and you'll see that in your epidemiology classes. It's usually the disease state that goes in your columns or rows, but it doesn't make a difference, but that's typically what's done. So let's put ethnicity in our row area here. I'm going to click on ethnicity, I'm going to move it to my rows, and I'm going to put sex of child in my columns. So we're interested in seeing if there's an association between ethnicity and the sex of the child which was born to the mother. Remember, we're working again with the NC birth data, so we've worked with this before. There's a description of this data set in the previous lab. This is a random sample of 800 mothers who gave birth in North Carolina, 2001, I believe. So we can leave it at this for now. Again, later on we're going to play around with these options slowly and gradually, but for now all we want to do is recreate this table in SPSS. So this looks good. I'm just going to click OK, and we have a crosstab here. So if you notice, the numbers are exactly the same. We have our crosstab which we recreated in Excel. Alright guys, so now we have our crosstabs which we obtained in SPSS. This is our output here from SPSS. You can confirm that the totals are the same. I copied and pasted this table into Excel for you. So we can get rid of our SPSS output and just stick with our Excel file. We should be able to read this table. It's pretty straightforward. We see our marginal totals representing, in this case, the total count for male children, the total count for female children, which should add up to our sample size or grand total. In this case, our marginal totals represent ethnic backgrounds of our mothers. So in this case, we see there were 523 non-Hispanic white mothers, 168 non-Hispanic black mothers, 82 Hispanic mothers, and 27 of other ethnic background, and that should add up to 800 as well. This section here represents the intersection. So for instance, a mother who was non-Hispanic black and had a male child. The count was 272, non-Hispanic white and female child, the count was 251. Those should add up to the marginal total. So the marginal total should add up to the grand total. The intersections should add up to the marginal totals. These should add up to the marginal total for male. These should add up to the marginal total for female. These should add up to the marginal total for non-Hispanic white. These should add up to the marginal total for non-Hispanic black. These should add up to the marginal total for Hispanic. And these should add up to the marginal total for other. And those marginal totals should add up to the grand totals. So we'll look and see how to do some simple probability calculations using these counts. The first thing, you should know what a sample space is. A sample space is all possible outcomes in our sample, depending on the categories that we're using. Now, in this case, our categories were our variables that we use were ethnicity and sex of child. So all these intersections represent all possible outcomes. We could have used different variables. For example, we see ethnicity has 4 categories. We could have used another variable which had 4 categories. In that case, we would have a 4x4 table. In this case, we have a 4x2 table. We can have 2x2 tables. It depends on the variables we use, and that will determine our sample space. So we would look at our intersections to see how many possible outcomes there are. We see there's 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes here. We should have 1, 2, 3, 4, 5, 6, 7, 8 outcomes. And these letters here you should see represent the outcome. For example, non-Hispanic white male, we see there were 272 non-Hispanic mothers who gave birth to male children. How can we calculate the probability for that outcome? We can see that our sample size was 800, so we simply take a simple proportion. We can say equal 272 over 800. And that's our probability, 0.34, for a non-Hispanic white mother giving birth to a male child in our sample. So now we wanted to know, for example, non-Hispanic white mother giving birth to a female child. That's our 251. And we could complete this table, and in the end, you should know all possible outcomes must add to what? It must add up to 1, because there are no other possibilities, so it must, in the end, add up to 1. If you find out that your probabilities are not adding up to 1, then you made a mistake somewhere, so you should go back and correct your math, and it should in the end add up to 1. So that is what we are doing right now. We're calculating all of our probabilities for all possible outcomes, and we're going to confirm that it adds up to 1. So let's use our sum function, which we've learned before. We're going to add these up, and we should get 1. So everything looks good so far. We have our sample space, all possible outcomes. We have the probabilities for each one of those outcomes, and we confirm that it does add up to 1. So now let's take a look at where we would be able to use these marginal totals. So if we were asking, for example, the probability that a child was male, and that's all I asked, irrespective of ethnicity, or depending on what variable is used for your cross tabulation. If you were simply asked for the probability that a child was male, irrespective of any other further categorization, we would simply look at our marginal totals. So let's say here I asked you the event that a child is male. Let A denote the event that a child is male, and I asked you what was the probability of A. So I look in my crosstabs and I see that the probability of a male child, I would look at my marginal totals. If I looked here, I would be wrong. These are not probability, this is not the probability of a male child. This is a probability of a male child and non-Hispanic white mom. So we are not looking here when we simply are asked for probability of a male child. So in this case, probability of a male child, we see the count is 418. Our sample size is 800. So we simply take 418 over 800, and that is the probability of a male child. Now look back at our sample space. If we see here the outcomes which include male children, we see 1, we see 2, we see 3, we see 4. Now if you were to add these probabilities, what do you think they would add up to? They would add up to this value, 0.52. Let's confirm that. So if I were to use my sum function again, we see one event, separate that by a comma, remember. This is a second event, outcome, excuse me, and final outcome. So this is the probability of the event that a child is male. We see several outcomes where a child is male, and we have probabilities for each one of those outcomes. We used our contingency table, our crosstabs, to calculate the probability a child is male by looking at our marginal totals. We saw 0.52. Now looking at our sample space, we are adding those individual probabilities, and we are going to confirm that it does equal 0.52. So next, if I were to say let B denote the event that our mother is Hispanic, and I asked you what is the probability of B, so you would look at your table, and again you see that I'm not asking you for anything else. I'm not saying Hispanic and male or Hispanic, simply what's the probability that the mother is Hispanic. So I know automatically I need to look at the marginal totals, where I see in the row for Hispanic I see 82, so I would calculate that probability as 82 over 800, and I would get 0.10. Now look back to our sample space. So in our sample space we see that there are 2 outcomes where the mother is Hispanic. We see here 1, 2, and those are these 2 outcomes here. We can sum those probabilities to confirm that we get the same probability. So we should be able to calculate those probabilities on an exam. That's pretty straightforward. I think no one will have a problem with that at all. Just do not make the mistake of looking in the wrong area for your values, and you should have no problem. Now let's move on to disjoint events or mutually exclusive events. Mutually exclusive events, for example, if we have 2 events, A and B, if A occurs, B cannot occur, and vice versa. Now that means that the intersection, the probability of A and B equals 0. So that is clear to see when you look at a Venn diagram here. The event that a child is male and the event that a child is female are mutually exclusive events. If a child is male, they cannot be female. So let's say using A and B, if male Let A denote the probability that a child is male, let B denote the probability that a child is female. If A occurs, B cannot occur, and vice versa. So when we look at the Venn diagram, we see that there is no overlap, meaning that the intersection is 0. The overlap of the two circles would have been the intersection. Now, in the crosstabs, the intersections we remember were here. So, for example, if we look at a Venn diagram, we can see it clearly that when there is no overlap between two events, A and B, they are mutually exclusive or disjoint events. When we look at a contingency table, we can see those intersections. And if you notice here in this contingency table, I made it so that the event that a mother is Hispanic and the child is male are mutually exclusive. So when we see the intersection, what do we notice? There is a 0 there. The probability of A and B equals 0. So that is the rule when we have mutually exclusive or disjoint events. The intersection equals 0. We should know that this represents intersection, probability of A and B. So become familiar with these symbols and formulas. There's a few simple ones that if you know, you should do fine with any questions of probability. So we can see in a Venn diagram what it would look like, and we can see in our contingency table what it would look like. And if on the exam, most likely I will give you a contingency table, and you will need to find out whether or not two events are mutually exclusive. This becomes important when we will go into calculating union of events, because if you look at this formula here for union, we see that A or B, we can see that this is the formula for union. You should know that the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. So if we were to look at this Venn diagram, we have, like I said, the probability that a child is male, it's denoted by A, and female by B. So the probability of A is this entire circle. The probability of B is this entire circle. So the probability of A and B would be A plus B. Now this third part of this equation, this is when there is intersection. Obviously, if these two circles were overlapping, there would be an area. If we simply added A and B, there would be an area in the middle which overlapped. And in that case, we would be counting it twice. So that is why we have this third part in the formula when we calculate union, because we can't double count that. We have to get rid of that part. So we add A and B and we subtract the intersection. With mutually exclusive events, there is no intersection. Probability of A and B equals 0. So what does this formula become? Simply the probability of A plus B, because they are disjoint or mutually exclusive events. So we could use this formula here for intersection, and it will equal 0. We will figure out how to do conditional probability in a second, and we will also find out how to do the calculations for intersection. But just know when you look at your Venn diagram or your contingency table, what you would need to see if two events were mutually exclusive, you would see a 0. And you could confirm using the formulas. We'll learn these formulas in a second. You see I worked them out for you. The intersection probability of A and B should equal 0. That is the characteristic of mutually exclusive or disjoint events. And that comes into play when we look at union as well, as I just mentioned. So we'll get into those formulas in a second, but just know when you see the Venn diagram and contingency table how to determine and identify mutually exclusive events. So next, let's talk about this part here, conditional probability. Now when we say conditional probability, we have the formulas here, probability of A given B or the probability of B given A. As you can see, this is simply a rearranging of this same formula, right? You see how we moved over probability of B, A and B over probability of B. That's what we see here. We simply rearranged the formula to get to this point. So when we have a contingency table, which is what you'll be presented with on an exam, and you're asked for conditional probability, there's a very simple way to do it. You can simply look in your contingency table. For example, if I asked what is the probability of A given B, letting A denote that a mother is non-Hispanic white and B denote that a child is female. So A given B, meaning probability of non-Hispanic white given female. So that's written here. Once you see this conditional probability formula, think of the words given B. So this is A given B, this is B given A. So when you're told what A and B represent, it should be clear. In this case, I told you A represents non-Hispanic white and B represents female. So this is non-Hispanic white given female. So when I say given female, you should automatically in your contingency table only pay attention to that column or that row. What if I was to say female given non-Hispanic white? As you can see, this is B given A, and we said A represents non-Hispanic white, B represents child as female. So B given A, once you hear the word given or you see the formula for conditional probability, this is A given B, B given A. A is non-Hispanic white. You would pay attention only to the row non-Hispanic white. You would calculate your probabilities that way as well. So let's say we wanted to find out probabilities conditional on gender. So given male or given female. So what's the probability of non-Hispanic white given male? So once you hear given male, I know that I need to pay attention only to this column. I don't pay attention to anything else. So what's the probability of non-Hispanic white given that the child is male? So now I see there were 272 non-Hispanic white mothers within the male category. So I would simply take that total divided not by the grand total, by the total male portion of our sample. So we see 272 was the non-Hispanic white mothers out of 418 in this case. And that we can do for every other category. So for instance, non-Hispanic white, non-Hispanic black given male, we would calculate as 87 over 418. Hispanic given male, 44 over 418. And other given male, 15 over 418. Alright, now an easy way to do that, we can do our equal sign. So now we're looking at our female column. So for instance, non-Hispanic white given female would be 251 divided by, now if you notice you're constantly dividing by your marginal total for male or female. In this case, we're going to keep dividing each category of ethnicity by our marginal total for female. So remember from last time, from part 1 of this lab, how do we do that? We can throw a $sign in and we see that the cell is D71. So we can keep that constant by throwing in our $sign, D71. And now when we drag down our formula, we can see that Excel did move down to D68, it went down to D69, and it went down to D70. So it went to the appropriate cells to get the counts for the ethnicity counts within female, but it kept dividing by D71. So you notice that? Every time it divided by D71, which is what we wanted. We wanted it to keep dividing by D71. Now these totals should, guess what they should add up to? They should add up to 1. So these totals should add up to 1. So we should get 1 as our sum for both columns. And we see that we do get 1 as our sum. So now what if I asked you to do to calculate the probabilities conditional on ethnicity? So male given non-Hispanic white, or female given non-Hispanic white, male given Hispanic, female given Hispanic. We will get back to that in a second because I showed you an easy way to calculate conditional probabilities when you have the contingency table. So what if I wanted to use this full formula? Now if we look in this formula, we can see two parts. One, we learned a second ago, probability of B is simply when we look at our marginal totals, right? When we see probability of A or B or anything like that, we simply look at the marginal total. For example, if I was to say that A indicated that a child was male and I asked you the probability of male, you would look at your marginal total for 18 over 800. And we just did that previously, two examples. Now the second part of this you can see is A and B, which we said was intersection. So how do we get intersection? That's the next section, and then we'll come back here and we'll use the full formula and we'll see that we get exactly the same numbers. So how do we use intersection? So to calculate intersection, the easy way to look at intersection is simply look in the cell and divide by the grand total, similar to what we did previously when we were looking at our sample space. It's exactly the same idea. So let's look at intersection of events. Now we know we should know that this here is the formula for intersection. We should know the formulas. Now notice again that this is simply the same formula rearranged. You should see that. It's the same exact formula, we just rearranged, we moved it around to A and B. We moved this B over, or this A over, and we're multiplying the two here. So we should see it's the exact same formula, just rearranged. Now how do we work with intersection if we have a contingency table, which you will have on your exam? So you can just simply take the proportion in which A and B occurs, the cell, the intersection. So for instance, let's say A indicated that a mother was non-Hispanic white and B indicated that a mother was male. So what is the intersection of those two events? Probability of A and B. You can simply look at the cell in which that occurred. So A and B, meaning non-Hispanic white and male, this would be that intersection, 272. We simply take the proportion 272 out of the total, 800, and we would get our probability of A and B, and that's how you would calculate intersection. Now if I wanted to do that for all of these cells, again, the easier way to do that, because we want to keep dividing by the total, right? So I would click my 272 divided by, and I would throw in my $signs for the cell E81. So E81, and I get 0.34. But now what I can do is drag this formula down, and I will get all my probabilities here. So you see that I could do the same thing for these cells here. Female 1 divided by E 81, right? Click enter and we should get our probability of 0.31, and we can drag that formula down and we should get all of our probabilities for the intersection. So this is the probability of male and non-Hispanic whites. This is the probability of non-Hispanic black and male. So we can see that these probabilities are the same as our probabilities from previous, which we calculated: non-Hispanic white male, non-Hispanic white female, 0.34, 0.31. We can see 0.34, 0.31, non-Hispanic black male, female, 0.11, 0.10. We can look back, non-Hispanic male, 0.11, 0.10, and so on. Same exact probabilities. Now, the sum of these probabilities, probabilities which we just calculated, should equal the probability of male. Do you remember what the probability of male was from our previous example? Probability of A, we said A is the event that a child is male, was 0.52. Let's confirm that the sum of these probabilities equals 0.52, and it does. Now, if you were to take a guess, what would you say that this probability would be? Now, remember that all of these intersections represent all possible outcomes, right? All of these intersections, these are all possibilities. So this obviously needs to be 0.48 because it would need to add up to 1, right? Okay, so let's see. Now we can take the sum of these probabilities and they will add up to 1. This should add up to 1. You should see that. Now, same way I got these marginal probabilities, I can get these marginal probabilities by summing the probabilities here. So if you recall, when we calculated the probability of B denoting the event that a mother is Hispanic, right? We did 82 over 800, right? E30, 82 over E32, 800, right? And we got 0.10. So now let's see what happens when we add up these two values, right? .10. So you should see that when you add up these two, you'll get the marginal probabilities, being the probability of non-Hispanic white, probability of non-Hispanic black, Hispanic, etc. So we could actually sum these and we can see, and what we're doing now is actually what we're doing, which you'll see in a second, is filling out our contingency table with probabilities. Now again, this should add up to 1, right? Either whether I add up the row or I add up the column, it should add up to 1. Okay, so now we are representing our contingency table with probabilities rather than counts. So we have a contingency table here with counts, and we have a contingency table here with probabilities. Now we can use the same rules, these formulas apply. Instead of using counts, we could use a table of probabilities. So we have a full table of probabilities here. Now we could go back to our previous section of conditional probability, and we know that the formula for A given B equals the probability of A and B divided by the probability of B. or probability of B given A equals probability of A and B divided by the probability of A. So let's get rid of these values here, and we'll use the full formula. Before we use the easier method, which you can use as well, but just to confirm that we get the same values. Now if you want to rewind to see these values, just let's see that we get those exact same values. And let's confirm that we don't need to use counts, we can use the table of probabilities. So what's the probability of A and B? Let's say we're looking for let A be the event that a mother is non-Hispanic white. So that's that. B be the event that a child is female. So that's this, right? So what is the probability of A given B? It's the intersection divided by the probability of B. So what is the probability of that intersection? 0.31, right guys? So we say equals 0.31 divided by, and the probability of B, we said B is the event that a child is female. So the probability of a child being female is 0.48, right? And what do we see here? That we have exactly the same value as before. Now we can try that now again. Let's say we were interested in the probability of A non-Hispanic white given B male. So we would do A and B divided by the probability of male. So that is the intersection A and B equals probability of A and B divided by probability of male. Right? 0.65. So now, as you can see, we can continue doing that for each cell, and in this case it will be easier again to add our dollar signs, because what are we doing here? We will, for each cell within this column, we will be using the formula for conditional probability. Now in the formula for conditional probability, we see that it's the intersection, meaning that cell, divided by the probability of B. So if we were saying given B and B being male, we would constantly be dividing by the probability of male. So we can keep that constant here, right? So let's say I wanted to keep I81 constant. So I81 is this cell here, 0.52. So what I want to do is, for this cell, the intersection, this part of the equation, A and B, is this here, 0.34, right? I77. And I want to divide by I81. That is the full formula, A and B divided by the probability of B. And I'm keeping I81 constant while I move down, because I want to keep dividing by the probability of B. So I can drag that down, and I will get my probabilities, my conditional probabilities. Same thing here, I want to keep J81 constant, and I'm going to drag that down, and I will get all my probabilities. Now again, what does that need to sum to when we're dealing with conditional probabilities? To 1, right? So let's confirm again, it sums to 1, and let's confirm that this sums to 1, right? Okay, to 1. Now we could again look at, let's say we were interested in conditional on ethnicity. So now we're saying A given B, B, for example, we can say is non-Hispanic white. So if and A is male, so what's the probability of A given B? That would be the probability of male given non-Hispanic white. So the formula remains the same. We see A given B equals the probability of A and B over the probability of B. So we said B was non-Hispanic white in this case. So now we can still use this table of probabilities and use our full formula. probability of A and B. It's still the intersection. It's this cell here, except now I'm going to divide by. So let's do the probability of A and B. In this case, the probability of male and non-Hispanic white is I-77. Divided by, now I'm saying given non-Hispanic white. Previously we were saying given male, so we were dividing by that column total, that marginal total. We're saying given non-Hispanic white, so we're only going to pay attention to the row for non-Hispanic white. So now when we divide, we're going to divide by the probability of B being non-Hispanic white. So that would be this here. And we would get our probability. Now I can move to this intersection here equals the probability of A and B. Again, it's that intersection. Now it's given non-Hispanic white, and I would divide by that, and I will get the correct value here. So now we can do that for each case. Probability of male given non-Hispanic white equals the probability of male and the probability of male given non-Hispanic black equals the probability of the intersection male and non-Hispanic black divided by the probability of non-Hispanic black. Right, now again we can do probability of female given non-Hispanic black equals the probability of the intersection divided by the probability of non-Hispanic black. And we can continue that here, so I'll fill these in. Probability of male given Hispanic equals the intersection, probability of the intersection divided by probability of Hispanic. Okay, we see equals probability of intersection divided by probability of Hispanic. Probability of male given other equals the probability of the intersection divided by probability of other. Okay, probability of female given other equals the probability of the intersection divided by probability of other. Now we have all of the probabilities here. We have the probabilities conditional on gender. So that was the probability of non-Hispanic white given male, non-Hispanic white given male, Hispanic given male, other given male, non-Hispanic white given female, non-Hispanic black given female, etc. And we saw that those columns added up to 1. Now in this case we were conditional on ethnicity. So now these rows should add up to 1 in this case. So now we'll see that they do add up to 1. They do add up to 1. As you can see, they add up to 1. They all add up to 1, right? So now we can add all those up and we can confirm that they add to 1, and we see that we can use the simpler method or we can use the full formula. It's up to you. You should see by now that you do get the same values. So far we've done conditional probability using the method of simply dividing the value, the count. So we did divided by the total in that column or row, and then we used the probabilities themselves using this full formula here. So we did the intersection divided by the row or column total, the marginal total here, the marginal probability, excuse me. So we've covered conditional probability, we've covered intersection. We can see now we can use again the intersection I showed you by dividing the count in that intersection by the total. That's an easier method, and I'll show you now that we can also use the full formula. So now we have in this table here probabilities, conditional probabilities. So if I were to ask you the probability of A and B, we can use the full formula to get the same values if you are interested in doing that. So for example, if I were to ask you the probability of non-Hispanic white and male. So let A be the event that a mother was non-Hispanic white and B be the event that a child is male. So we're looking for the probability of A and B. The probability of A, non-Hispanic white, given male, times the probability of male. So we have a table here of two tables of conditional probabilities. We see a conditional on gender, conditional on ethnicity. So I said A equaled the probability of a mother being non-Hispanic white, and I said B was the probability of a child being male. Event that a child was male. So probability of A given B is the probability of non-Hispanic white given male, and we see that probability here in this table here. This is conditional on gender, right? So this formula here we can use, we can say equals this value here. Okay, I-67. Now we're multiplying by probability of B. We said B child was male. In this table here, we see that the probability of male is 0.52, so we can click on that. And what do we get? We get exactly the same value. So we can use the full formula, or we can use a simpler method. We will get exactly the same values. Now in the answer key posted on Blackboard, these tables are filled with the values using both the formula and the simpler method. Same thing for conditional probabilities. When you look in the answer keys, you'll see that one table uses the simpler method and one table uses the full formula. So look to the answer keys and click on the cells, and you'll see within the function box here that you'll see in one table I use the simpler method, in the other table I use the full formula. So look at the answer keys, decide which one you feel is easier for you, which one makes more sense, and use it. So those tables are filled out in the answer keys. Now I'm going to move on to union. We mentioned before when we were talking about mutually exclusive events or disjoint events that the equation, this part of this equation would be 0, since the probability of A and B would equal 0. So in that case, this would simply be the probability of A plus B. But this full formula always applies. So remember that these you would end up getting 0 for this, and it would end up being simply probability of A plus the probability of B. So we could figure out probability of events, and the way we would say this would be the probability of A or B. So it's either or occurring, one or the other. So which would be, again, adding, when we look at the Venn diagram, the probability of A plus the probability of B. If these were not mutually exclusive events, these circles would overlap, and there would be an area where we would be, if we were to simply add the two, we would be adding that area twice. So that is why you see this part of the equation here. We need to get rid of that. So when we calculate, for example, let's say that A was the event that a child was male, and let's say B was the event that a mother was Hispanic, and I asked you what's the event of A or B. I could calculate that by first going to what is the probability of A being a child is male. We have a table here of probabilities, right? So that was 0.52, okay? And I'm going to add the probability of a mother being Hispanic, we said was 0.10, right? I need to subtract this intersection A and B. Where was that? In this table here, you see A and B. We said male Hispanic, the intersection is here. So I'm subtracting that. And I will end up getting the union of the probability of the union, which is 0.57. And that is A or B. That is how we calculate union. So now it should be clear that you can use this table of probabilities. These tables of probabilities make things easier. You could use the counts. You could use having these contingency tables in front of you makes things a lot easier. On the test, I'll give you that. And then you could on your own create these tables of probabilities from these tables of counts. So we just saw how we could create several tables of probabilities. We have a table, Crosstabs, which we obtained from SPSS with our counts, and we created tables of probabilities with conditional probabilities and intersections, and we were able to use those probabilities for all of our formulas. So it makes things a little easier when you have those tables in front of you, but if you did have a table of counts, or you'll always get counts, so you can either create your own table, but I doubt you'll have to do that on an exam. But with those counts, you should be able to create all these tables of probabilities. And with those tables of probabilities, you would be able to calculate all of these formulas. And notice that these formulas are simply, we're rearranging the same formula and using those same probabilities in each case. And the last part of this part 2 of the lab is going to determine whether or not ethnicity and sex are independent events. So now there's a few rules for independent events. Recall that the probability of A and B, right? We say that the probability of, when we were doing intersection, probability of A and B equals the probability of A given B times the probability of B, or probability of B given A times the probability of A. Those would equal one another. So we have those formulas rewritten here. Now, with independent events, the probability that one event occurs is not affected by whether or not the other event occurs. So the probability of A given B will equal the probability of A. And the probability of B given A will equal the probability of B. So when you have those two, when that is the case, this formula, if you notice, becomes simply A times B. So if the probability of A given B equals the probability of A, that's this part here, this formula for intersection A and B equals A times B. Similarly, probability of B given A times probability of A, if B given A equals B, probability of B, then this formula becomes probability of B times probability of A. This formula applies only for independent events. This formula always applies, whether or not events are independent, it doesn't matter, because this will always end up equaling A, and this will always equal B. So using this formula here, we can test whether or not two events are independent. If this formula applies, if A and B equal A times B, probability of A times B, then they are in fact independent events. So we can test using those rules whether two events are independent. If the probability of A given B equals the probability of A, or probability of B given A equals the probability of B, or probability of A and B equals the probability of B times the probability of A. So let's determine whether those are true in our case. What's the probability of A and B? Remember, we learned how to do intersection. Remember how we did intersection? We simply calculate the intersection is the count, and that, let's say, the probability non-Hispanic black and having a female child. So non-Hispanic black and female is this cell here, right? 81. So we would do 81 divided by 800, right? And that was 0.10. So now we need to determine whether or not how do we calculate A times B? Remember, probability of A. If we're saying A is the probability of being non-Hispanic black, irrespective of gender, we were looking at our marginal totals when we were calculating probabilities like that, right? So we would just go and equals the probability of non-Hispanic black is 168 over 800. Now we don't need to use the counts because we have a table of probabilities here. Remember, probability of non-Hispanic black 0.21, right? And we're going to multiply by the probability of female child. And probability from our table above of a female child was 0.48. So if you see here, I'm doing the cell K78 times J81 from our table here. K78 times J81. This is the probability of A times the probability of B. So if this equals 0.10, then those events we can say are independent. If it does not equal that, then they are not independent. So actually they are independent. So now these all should also apply. So the probability of A given B. We said A is non-Hispanic black and B is female, so we're asking non-Hispanic black given female. So once I say given female, you should know that you need to pay attention to this column only. So what's the probability of non-Hispanic black given female? It's equals non-Hispanic black 81 divided by, not the grand total this time. Remember, conditional probabilities, the easy method, just divide by the total in that category. So 382, right? So we have 0.21. So now that should equal the probability of A. We said the probability of A was non-Hispanic black. So that would be 168 over 800. And we have our table here for non-Hispanic black. The probability is in fact 0.21, so we can confirm that the probability of non-Hispanic black is in fact 0.21. And again, probability of B given A. So B, remember, female. So female given non-Hispanic black this time. So once I say given, whatever comes after that word given, you would pay attention now in this case to this column only, because this is given non-Hispanic black. We said A represented non-Hispanic black. So we're asking not for A given B this time, we're asking for B given A. So it's female given non-Hispanic black, so it's 81 over 168. So equals 81 over 168, and that equals 0.48. Now the probability of B, we said B is the fact it represents a female child. So what's the probability of B? We simply look at the marginal total, 382 over 800, or we can go back to look at our table of probabilities, and we said the probability of a female child was 0.48. And we can calculate that now, the probability of a female child, 382 over 800, and it is in fact 0.48. So these events we see are independent from our sample. Now in a later section we are going to start talking about inferential statistics and statistical significance, and we're going to start doing hypothesis testing. Then we will come back to this because there is a next step after this. We do a chi-squared test. That's when we're going to start talking about inferences about the population. Just because we see our sample, in our sample two events are independent, it does not mean that in the population that applies as well. So we will start doing significance testing and hypothesis testing, and the next step to this would be a chi-squared test. So we will get to that later on. But this concludes today's